Look, Max, they've reopened the Ferris wheel. Oh, but we're right by the roller coaster too. Oh my, I don't know what to choose. Are you sure there isn't one attraction you prefer? Oh, come to think of it, we can always ride them all. Max? Max?
Oh, my popsicle! Why is it melting so fast? I don't even have time to enjoy it.
Are you really that surprised, Max? It's summer, it's hot. You've got to hurry up and eat it.
Sure, but look at that child over there. His ice cream is still intact.
Try to focus a bit more. It's less exposed to the sun.
Are you sure it can have that much of an impact?
Well, we can try to compare them from a system modelling perspective. When you study a system, you first have to define it carefully and to make all the assumptions about what's going on, but also about the physical phenomena occurring. Here, we're going to consider the whole popsicle as our system. To simplify a little, we consider it homogeneous. It receives energy as radiation from the ground, the sun, and the air at a certain temperature.
When you say we consider the popsicle to be homogeneous, does that mean we forget about the fruit bits, for example?
Exactly, because they involve more complicated calculations. Of course, this assumption will affect the accuracy of our model, but it's a fine balance to strike.
On the other hand, with all the elements affecting our system, it's a bit difficult to see clearly, don't you think?
That's where system modelling can help. We use a block diagram. It's a simplified diagram of how a dynamical system works. It doesn't give any technical details, but it does help us understand how everything interacts. All the considered phenomena are described by more or less complicated equations. But the important thing to remember is that we can't always solve them directly. I mean, analytically.
So we can't describe the evolution of our popsicle after all.
We can, but in an approximate way with numerical computations. In systems modelling, a mesh is like breaking a big shape into many small pieces, so a computer can do computations on each piece. This helps us understand how things like heat, movement, or fluids behave in real life. The smaller and better shaped the pieces, the more accurate the results. And finally, we get this curve and this evolution for your popsicle.
Whoa, it's super efficient in fact. But wait, look, it's not quite what happens in real life.
Indeed, a model is never perfect. We had to make choices. For example, when we considered that your popsicle didn't contain fruit bits.
But in that case, there could be an infinite number of models with an infinite number of assumptions. How do you choose?
Fortunately, there are plenty of ways to evaluate a model and select the best one. We can compare our model with reality using criteria such as the mean squared error. For our popsicle, for example, we compute the distances between some particular points of the popsicle's surface and its actual centre of mass. We take the square and calculate the average, but this is not the only method. Sometimes models can be biased, which means that the model makes systematic errors. So, to refine the way errors are taken into account, models can include uncertainties. Instead of having a model with only precise points, we add an interval where the value can probably be.
Okay, I understand now. But do you think this could work for even bigger popsicles?
What do you mean?
Take land glaciers, for example. Because of global warming, they're melting little by little, which could cause sea levels to rise. Couldn't we study them with your model?
We can always try. For example, we could track the thickness of the ice flow, which is similar to the melting of glaciers, but it becomes much more complicated. The system is bigger and a lot of new factors appear. Today, researchers in this field have models that are more or less effective, enabling them, for example, to predict the theoretical thickness of the ice flow in the next few years, taking into account its melting.
Why isn't there just one curve, but several?
On such complex systems, several models and assumptions can be used, which gives us several different curves in the end. This allows us to anticipate different possible future dynamics, from the worst-case scenario to the most positive.
We can only hope that this is the one that happens.
That, Max, is up to us.